pumped that you have joined us for this amazing event, and we hope that it will be quite a learning, motivation, and get you started in doing deep learning in R. So without further ado, I present to you Sigrid Keydana, an applied researcher at RStudio. And Sigrid, the floor is yours. Thank you so much.
Yeah, I'm very happy for you invited me. Thank you very much. And I'm very happy to be talking to everyone tonight. I think I can say tonight, right? Because it's for you, it's also evening. Should I directly jump in with the talk? Or do you have anything in advance?
Oh, no, not really. You can get started.
Okay, how should we do it with questions? Are people writing questions in the chat somewhere, or should we just answer questions after the talk? So I just do the talk, and yeah, what do you prefer?
Yes. Yeah. So what we planned is after you give the talk, people will be writing questions in the chat.
Okay, great. So I don't see the chat for now, but I think I can open it later, I guess, or perhaps that's also better for concentration. So, okay, then after the talk, I'm gonna open the chat and yeah, read the questions. Okay, then. So is it fine if I share my screen now?
Yes, Sigrid.
Okay, and I'm gonna do that. That was here. Okay, entire screen, that one. Share. So I hope everything is okay. Just one last question. Do you see my screen? Everything fine? Then I'm gonna start.
Yeah,
I can
see it.
Okay, then I'm gonna start. So again, thank you very much for inviting me to talk about deep learning with R. Now I'm really gonna jump in directly with this talk. When we talk about deep learning, we necessarily talk about data, because deep learning is facilitated by big data. There would be no deep learning without lots of data. And now really, there's two phases to data, really. I mean, data is a good thing in one way, but data is also a threat, right? And let's start with a good thing. I mean, data is good in that it helps us make empirical decisions, as opposed to just inferring stuff or saying what we think, like gut feeling. So data is good because we can verify things, right? Also, there are so many problems we hope we could solve with data. One thing I'm thinking about often is climate change. So perhaps deep learning, machine learning could help us with mitigating that somehow. And so deep learning, why am I talking about data, right? Because for deep learning really needs lots of data, basically. I mean, so example applications often are programmed not with a few data, and that's also nice for learning, but where deep learning really shines is when it has lots of data. And the other thing deep learning really needs is compute power. Also, there are differences, but in general, these two ingredients are just super important. And of course, there are algorithms for deep learning. And yeah, so the last thing I haven't really filled in there. So other ingredients, well, actually, there is a lot of trial and error to deep learning. So one tries out a lot of different hyperparameters and yeah, sees what works best. So that's all the good thing of what we can do with data. But, and I actually increasingly think it's important to say that think it's the first talk that I'm really saying this, and I'm not going into any details here in this talk, but the way the word is developing recently, we really have to think about this more and more, I think. So what can go wrong, right? With ways machine learning, and especially nowadays deep learning, is being applied. For one thing, application of machine learning, that's okay, I'm going to say AI, right? This artificial intelligence, AI, like this hype word. So AI can enhance inequalities, broaden gaps. One thing which is not really deep learning, but which kind of comes to mind in these COVID times, and for me, is we see how now with COVID, inequalities get broader everywhere. So I think also inside countries, between countries, but also in countries, inside countries, and so inequality, right? And also those people who are already at a disadvantage in a society, it can really easily happen that they are even going to be discriminated against even more by application of deep learning. And what you always hear, like, there's bias in there somehow. How bias? I mean, probably many people have heard about how data sets can be biased. So like when algorithm was only trained on some sort of people, not on others. And so yeah, okay, the data set is biased, and then it works less for that group than for that group. But bias is really not just about data. It's also algorithms that can be biased. Like if you use a loss function for optimization, then this makes a difference which loss function you use. So it really makes a difference. And of course, people, societies, and whole systems can be biased. And as this talk is not about that, but I just feel I don't want to do this talk without even talking about this, I'm just putting here some links without going into any detail on some stuff I have read or watched recently, like a tutorial. A video tutorial is the very first one, and the other ones are 2 articles, and there's also like the classical books like Roy Benjamin's Race After Technology or Data Feminism. So I'm just saying we should increasingly be aware of the consequences of what is being done with deep learning. But I think I leave more on that topic for some future, so to say, and I'm not going to jump into the topic of the talk. I mean, but that also really is the topic. So I just think it's really important to talk about this. Perhaps one example for perhaps some people have already done something with object detection. There's one deep learning model which is kind of the one flagship of object detection. It's called YOLO or YOLO v3, you may have heard. And like I think half a year ago or so, the creator of that model tweeted something like he stopped working in computer vision because of how that stuff is being applied, like for surveillance, monitoring, tracking people. So that's for the impact part. Now, still, that sounds negative, but if one does not know what deep learning is, one has no idea what is the threat there. So what is possible now? What can people do with deep learning now? What can happen in the early future, and what to be aware of? All these things. It just, if you know what deep learning is, so I guess I don't really know, but I think my audience might be pretty mixed. Like some people perhaps have not done any deep learning before, others have. So now to those who haven't, just if you have an idea what that is, you're better prepared for how it's used in the world, right? And also, of course, that fourth point, what could be used to make this world better? I mean, in the end, it's also about what we can do. So it's, I mean, we can't always influence what the others are doing with technology, but we can try to do our best ourselves, I guess. So there's really good reasons to learn about deep learning. Now, what is deep learning? Well, just one way to kind of classify that. I hope you see so for the pictures which I took from like books or articles, you always find the source here in the slides, and there's a classic book by Ian Goodfellow and collaborators on deep learning, which is also available online. And I think I'm linking to the online version of the book. And the way he classifies it, like the outer, like the whole thing, right? This is AI. So perhaps that's a bit surprising, but AI is not really, originally has not been the same as deep learning. Now we kind of use it nearly synonymously, but it's not really. There's the historical approach was rule-based learning. So basically you code up rules, or symbolic learning, like expert systems. So AI historically was a broader approach, right? And then what Goodfellow is doing here is he's zooming in, like some subset of that would be machine learning, and a classic example like regression, logistic regression. Yeah, probably you may have used something like that before. And then he zooms, he zooms in further, goes to representation learning. What's implied there? Well, when you do a regression, you just fit a model, right? And in representation learning, before you really fit that model, you try to extract learned parameters. Features. Guess I have. You learn features is also, for example, in computer vision. Before deep learning, there were ways how people extracted features from an image and then ran a classifier, for example, on it. So, and then again zooming in, we arrive at deep learning, and this is what it's about today. So what's a neural network? There's this web page, it's called TensorFlow Playground. Again, it's here a clickable link. Or, I mean, okay, if it's slide, I put the slides on RPubs, by the way. So, and then of course you can't probably click the link. Actually, I don't even know if you can click the link. Anyway, there's the link. And so what's a network? Basically, we have three parts here. We have inputs. Here, the inner part of the network, which could be of any size, basically, and any internal structure. So it doesn't always look like ordered and flat like that. And we have an output. So we feed in something, and then some black magic happens, and some output. And that can be used for regression, for classification, basically for the same things you would do with other forms of machine learning. Only that here, there's a lot of stuff happening in these so-called hidden layers, right? And what you can do when you go on that web page, you can play around with it really. So you can add and remove neurons here. So these units are the neurons. You can also add in more input features, more outputs, and then tune some of this stuff here at the top, which I'm going to talk about in a second, and play around with it. So if you haven't been doing deep learning before, that's a nice place to start, just to get some intuition. Now, why is deep learning so successful? And that, in one slogan, would be because representation, so how you code things, really matters. How you code it up, how you symbolize it. And here, imagine that here on the left, the task is to pull apart two classes, like these blue things from the green things. And of course, if you want to put something apart, it's easy to draw a line between them. But here, really, with that representation, you really cannot draw a line anywhere, right? Because, yeah, it doesn't work. But now, if you just do a transformation of coordinates, like from Cartesian to polar coordinates, you see that now suddenly you can just draw a line here. So you can say, oh, these are the blue ones, and these are the green ones, and that's that. So it really matters how we represent our data. And the thing with deep learning is we don't have to think ourselves how to represent that. That's exactly the task of the network, to learn it. So here's another example from that book, another image from that book, where you see you want to classify that picture of a woman, and you get just some pixels, right? So some colors, that's basically everything, colors at special places. And then you have several layers in this neural network, 1, 2, 3 in this case. Normally it's more for image classification. And then at every layer here, the representation gets a bit more, let's say, less granular. So here we have just something like edges, basically, in that direction or in that direction. Then this here is already a bit more complex. There's a corner here and something circle-like, and yeah, whatever that really is. And here he jumps up really quite a bit, and there we already have parts of objects. Here you see like part of a tree. Actually, there's already part of a person, and so on. So this is why you have these many layers in such a network. So at every layer depth, the representation gets a bit more whole, like object-like. So, and in the end, you would classify that. And the thing really is, the network is trained to do that stuff. Now, one thing you need when you start, or one thing you need to learn is just, so I don't think you need to learn lots of math, but you just need to know what people are talking about, right? So, okay, what do we talk about? First, we talk about neurons here and layers of neurons. So these are the individual neurons here, these circuits, and the layers is this is the input, and then hidden layers and the output layer. So that's one thing. And what do these neurons do? Well, as you see, all these arrows here, they all get inputs from some other neurons. For example, if you look at this one, it gets inputs from that, and so on, from all these basically. So in this case, we even say it's a fully connected network, because really every neuron gets input from everyone else. And that's not necessarily so always. Anyway, so all that stuff comes in here. Okay, so this neuron gets some information. It somehow adds it up, aggregates the information, and then it also does some transformation. I'm going to say what that is soon. So it does something with that information, and then it passes it on to the next layer. Here, like all these connections, again, it sends that aggregated and transformed information to all these neurons in the next layer. And then the same thing goes on like this, and in the end we have the output layer, which also aggregates and transforms and outputs in that case. So that's one thing. That's the neurons and layers of neurons. Then we have the activations, and we saw these edges between neurons, and now the activations are the values passed from one neuron to another, right? So for example, here we have one neuron, and it says to the next one, oh, my output, after I did all these transformation stuff, you don't need to know about that. My output now is 22.2. And okay, I think there's a typo there. Just see, this should be another neuron, because it sends the same output to the others as well. So sorry for that. That's not layer 1 neuron 1, but it's a different neuron. But the point is to know the activation is the information passed on, and it's obtained normally by applying an activation function to the aggregate. And there are different activation functions which you see in the deep learning frameworks. But yeah, it's important to know what an activation is really when people are talking about that. And then another important ingredient is the loss. What's the loss? Well, that's like in machine learning, besides deep learning, it's the difference between the target, the ground truth, and the output of the network. So again, here is an example like here's one output neuron. I say 0.33, and the target, it should have been 25. And here again, I can have different loss functions, right? So I could either compute the absolute error, or I could compute the squared error, and there are many more. So there's always choices to make. But the important thing is, what is the loss? What the difference between the target and the output? Then we have the weights, and the weights are the connection strengths between the neurons. Here is again this example with the two neurons. And here really it is not a mistake. This is really okay that the connection between this is the same neuron, but it's the weight of its connections to that neuron and the other one are different. So the first connection is kind of more important, if you want, like the second, than the second connection. And the thing, what makes it deep learning or what makes it neural network is that these weights are really learned by the network. So that's really the difference to some rule-based or design stuff. We don't have to find these weights ourselves. Okay, and then how are these good weights found by the network? That's a question of optimization. Again, optimization we also have in other machine learning techniques, but there is one special thing here, and that's this famous backpropagation, right? Because now the loss is computed at the end of the network, like the output and the target, like I said, is the loss. But we have to adjust the weights all before that. So at every point in the network, we have these, at every edge in the network, we have these weights, and we need to find good values for that. And this is done by backpropagation. Here's a very nice post. You can read that later. On backpropagation, how it's done. And again, we want to know what are the important terms. Another important term in practice, again, what you need when you really write some code is the optimizer, because that is the guy, so to say, who computes the weight updates. Because we have the loss, so we know, okay, we need to adjust something, but how exactly to adjust, that's the job of the optimizer. To just see all the thing in one. And here I should also mention that this picture is taken from the deep learning book. You probably have heard of these two guys here, like François Chalet, he's at Google, and he basically wrote the Python version of the book, and then JJ, he ported that to R. He wrote the R TensorFlow implementation. And he also co-authored the R version of the book. Okay, and this is where this picture is from. Here you see again, we have an input. We have these layers of neurons, which have all their weights. And then at the output, we get some predictions. We compare those using a loss function with the true targets. We compute the loss, and then the optimizer goes and updates those weights. And then we do the same thing for, some time. Like, so we get good weights. So that basically is deep learning in an essence. Now, I'm just gonna drink a little. Hot day here too, actually. Now you're thinking, okay, that's all deep learning, but what with R, right? Can we do that with R? And probably you already know that you can do TensorFlow and Keras from R directly. Here I have a collection of useful links. Well, the one thing is, just to get started, is this I'm not going to click this now, but we have this tensorflow.rstudio.com, and there are guides and tutorials, and I think the best place is really to start with the tutorial. I mean, you need to install it. I'm going to say something about that in a second, but then you really start with some simple tutorials. I mean, simple, I don't like to say simple. I mean, it's just nothing's ever simple when you start with it, I think. So I don't really mean that. But anyway, I'd start with the tutorials. That's that. Then also we have GitHub repos for all that. So we have for TensorFlow, we have for Keras, and later I'm going to mention some other projects. But first, like if you have a problem to get something installed or something doesn't work, then just open an issue in one of preferably these repositories. Actually, we don't really always answer everything so quickly because it's just so much else that has to be done. But we also always try to find more people also jumping in with these issues, but that's something I'm going to talk about later still. So I'm going to come back to that. Then we have have a blog. This was called the TensorFlow blog until, I don't know, sometime in April. And now it's called the AI blog, and it has stuff not just on deep learning, but also on distributed computing. So it's Sparkly R, for example. So it's really pretty broad in topic. Also different people. I mean, I do write for the blog, evidently, but it's not just me. And we also always welcome external posts, by the way. So we are very happy when we get a PR for a post. And then there is this book. I mean, definitely to really go to really understand more about what you're doing, I really recommend this book. And I have one thing to add. There was a significant change in the TensorFlow framework between this first edition 2018 and now, which is the advent of TensorFlow 2. And there will be a second edition of the book. Actually, we don't really know yet when that will be available. One of my colleagues, Danielle, and I are going to do that later this year, but we can't really promise exactly when it will be there. Just to say, things in this first edition may need some tweaking at the moment, but we hope to get the second edition ready soon. There's also a YouTube channel. Now, I have to say, I think we have more videos okay, and that's not true perhaps, but we also have a lot of videos on distributed computing there, not just deep learning, but also on deep learning installation and how to automate stuff. So there's that. Now I need to say something about installation. Installation normally should be really easy. Now the thing is, there's lots of dependencies, not R dependencies, but it can depend on. It can sometimes be more tricky than it should be. So it can depend sometimes with certain operating systems. So in that case, just open an issue in the repository. Normally, really, how it should look, you should just need to do the following things. So you need the TensorFlow package. So installer packages, TensorFlow, and installer packages Keras. And then for many examples, you will need this package TF datasets, which is let's say, the current way of get data into TensorFlow. So these 3 packages you probably really need, and then you just here load the TensorFlow library. And there's one thing you need to do still, you know, because TensorFlow, the R package, does, when you install that, you don't already have the Python framework backend, and you need that. So when you do install TensorFlow, you get the Python backend. And this will, okay, this needs Python definitely. And now it's like dependent on your operating system, and Python anyway can be a bit of a tricky language with the environments. So nowadays, by default, this will create a miniconda. Miniconda is a Python distribution, lightweight distribution. So it will install that miniconda thing. It will install a dedicated environment, which will be called RReticulate, because reticulate is the wrapper, or is the, how to say, yeah, when we do Python stuff from R, we are doing it via reticulate package. So actually you will need this too, but I guess it gets installed as a dependency. And then if you don't have that miniconda already, you will be asked whether you want to install it. And normally, probably you should. So the base case would be you just really say yes, and that's it. So normally that should all work. Just do this one thing. And then as a test to see, for example, what version did you get, and also get some more information where that Python sits now, you can do this TensorFlow TF config, and it will tell you. There's one thing which is a bit confusing for people who have used Keras before, like, I don't know, like more than for some longer time, you know, before this change to TensorFlow 2 and all. And you also needed to install, at some point you need to install Python Keras. You don't need that. So don't normally worry about Python Keras. This will install Python TensorFlow, and today there is this Keras is integrated already in TensorFlow. So basically this should be it, but if you have problems, please create an issue. Now let's see. Let's create a network, right? So there's this nice package by one of my colleagues, a different penguin species. Basically, it's a drop-in for the iris dataset. So it's a nice little small dataset, and I'm using that for demonstration. It's in that Parma Penguins package, which you would need to install. I think it's on cron now already. I think, yeah. And what do we do? Well, I mean, deep learning is really a lot like machine learning in many respects. So we need to get our data in the form we can work with that. So we get a data frame or a tuple from, because it's like tidyverse family stuff. But now what we really need, we just want numbers, right? So numerical input we need. If it's categorical stuff, we like if it starts from 0. And here in these penguins, there the character data are already factors. So all I need to do for that is I convert these factors to numeric. And here you see some example outputs where I just have how many? 8 variables. And they are already in processable form for a neural network now. And our task, what you want to do is you want to predict the species. There are 3, like with iris, 0, 1, 2. And all the rests we want to use as predictors, right? And so we have stuff like, this is, I don't even know which part of or how to, I'm not sure about the right word. Anyway, this is some kind of anatomical feature, that 2, that 2, that 2. There we have sex here, which is also numeric in a way. And here we have island is coded, but definitely it's a categorical variable, right? So it's even if it's numbers now. So just we see our predictors are not all numerical, but also categorical. So this island is not really, I mean, island 2 is not bigger than island 1, right? So, and what do you do there? In deep learning, there are basically two options. You can either one-hot encode the stuff, which means that a one-hot vector is a vector where one position has a 1, yeah, and all the rest is 0. And if you have, in that case, you would have like a vector of 3, and then if it's island 1, you have a 1 in the first place, and if it's 2, you have it in the second place, and same for the third. And in deep learning, one thing which is popular is also the second way, which is called embedding, but this is definitely something for another occasion, but just so you know it exists. So we are going to do one-hot encoding here, and for that we can use this top categorical in Keras. Here's a bit like technical stuff how you have to do it, but basically you can use this Keras function for that. And further, what we do, so what are we doing here? X will be our predictors, which we transform like that. Y will be our target variable, and that will be species, right? And we also transform that to categorical. Then we split it into training and validation. I mean, this is a very, very small data set. I think it's 300 something. So if you have enough data, what you do is you have 3 groups actually, like training, validation, and test. I mean, train and test you probably know from normal machine learning. Validation we use during training just to monitor what's happened on data which are not at the same time being optimized, right? So here I don't have any test data, but it's, I mean, just an example use case, but I used all the data to have a training set and a validation set, so I can show you how that monitoring optimization looks. Okay, now that was data input, right? And if you ask me, that is often the most tricky and hard and error-prone and time-consuming thing. Of course, sometimes you can just get your data, which is all looks great already, but I mean, in many ways, it's like really like data science overall. It's a lot of just data wrangling. Anyway, now let's say we've done that, and we're gonna define the network. Now in Keras, we have 3 ways to define a network. And if you've used Keras before, chances are you probably use this model, Keras model sequential, which defines the model as a sequence of layers, right? This is the easiest way, but it is not always, it cannot do everything, but if it can do what you want, by all means do it, because it's just easiest, yeah. And so I personally always try to keep things as simple as I can, because I know I'm going to make mistakes otherwise. And so if you can use it, then there's the so-called functional API Keras model. Not going into that there, but that's very nicely described in the book, for example. And this here is the most recent one, this Keras model custom, and turns out, so I'm using it quite a lot, so, because it's a bit more Python-like. It feels Python-like. So if you have done deep learning in Python, this should feel pretty familiar, actually. And it just gives you a lot of flexibility. So, for example, in blog posts, I often end up just using Keras model custom for some reason. Yeah. Okay, that said, we're now going to use this Keras model sequential. And here I'm in these titles, I'm trying to refer back to the actors I introduced in the beginning, like what do we need to define our training procedure? We need a model. That's clear. We need a model. And so the Keras model sequential is a listing of layers. We have 3 layers, bit more than 3, sorry, 3 dense layers. Is that right? Yeah. So a dense layer is just a layer where every neuron from one is connected to the into all neurons in the previous layer, into all neurons in the following layer. So this basically you see all the time, layer dense. You say how many units, neurons, I said before, called that before, it should have, and this activation function. This was the way the neuron aggregates, what it does after it has aggregated the incoming information, the way it transforms it. So of these layer dense, I have 3, in fact, layer dense. And the output layer is also a dense layer. And what we say here, we have 3 units, and this is because we have 3 species. And we will want to output per species the probability that it's that species. And for such cases, if you have multi-class classification, so more than 2, you often see this activation equals softmax. This is just a way to convert the output values into output probabilities, basically. So that's our network. There was also this layer dropout. Can't go too much into that here, but yeah, basically it's always like normal machine learning. We always are in danger of overfitting. Actually, perhaps we are even more because we often have much data. We don't. No, that was wrong. Sorry. We have much data, but still we are in danger of overfitting. And that's for the reason that we often have many parameters. So neural networks have tons of parameters, which can all be set so that you very nicely fit the training data, but then what happens to the test data? So to put it correctly, even though deep learning often works on much data, it still can overfit. And so we have different things we do to prevent that. And one thing is these dropout layers where just at random, some proportion of the connections are kind of destroyed during training, not permanently, but on one pass through the network, they are not taken into consideration and dropped out. So it's not the only way you can say, like in machine learning, you say regularized in your network, but it's one very popular and successful way. So this is why I added these 2 dropout layers here. Okay, and that's basically the complete neural network to classify the penguin data. Now, what else do we need? If we think back, we always need a loss function because we need to say, like, if we have an output and I have a target, the network needs to know how to compute that difference. What is the difference between the output and the target? And so if you use the sequential API in Keras, you take that model which you defined above, and then you say compile and put some stuff there. So it's very handy and you don't have to write much. And one thing you put there is this loss equals categorical cross entropy, and this is a form of loss function which, like it says, it computes the cross entropy, so some kind of mismatch between output and target. And use this if you have more than 2 categories. Otherwise, you would see binary cross entropy. Yeah, you see, these are the ones for categorization, which you classification, which you see most often. Okay, so that is the loss function. We have that. Now we need an optimizer, and as you see, I just put it in the line below. So it also goes into model, into compile, and Well, this is one of the more popular ones. And another one is a so-called Adam optimizer. So often you see either this one or Adam. I think you see Adam more often, but this is something you can vary, but it's, yeah. Normally I just start with something which is used often, because if it's used often, it's probably works fine, right? And the third one, I didn't say much about that, but you also put in compile some additional metrics you want to monitor. For example, the loss. I mean, this is not really for humans. That's not very readable, this cross entropy, but something like accuracy, like the percentage of correct classifications, that we can kind of picture in our head better what that is. So now, yeah, that's that. And then already these were our actors, and now we can already start training here. And I already said that because otherwise, if I leave it out, I mean, here this data set is really small, but I just show it because it's important why we train, because the training set is the data we optimize on. We always want to monitor on that validation set. And now when I do training, I call fit on the model. I pass it the data. And I also say validation data and pass that in. I also say how long to train, this is the epochs, and what batch size to use. And here you see one example output from this. You will see if you use RStudio, you will see that in the viewer pane. Actually, you would during training, you could see how the loss develops. Hopefully it goes down, and you see that separately for the training and the validation set. And you also get the accuracy displayed here. Yeah, and that's basically it. Now, yeah, let me just take a. So that was our first Keras network, right? And now I want to show something different. Different architecture, different application. Perhaps you, again, actually I need to be cautious, because I'm now going to say that deep learning is also used to generate stuff, right? Generate images, fake images, also generate text. I don't know if perhaps you followed all this GPT-3 stuff now, like with the language model producing answers to questions which may sound very realistic, or actually do sound realistic. So it's not like totally clear how that's a positive application, but neural networks are used to generate stuff. And the architecture is interesting, actually, is generative adversarial networks. So there, the background is kind of from game theory. I have two actors, or opponents. I have one guy called here the generator, and I have one guy called the discriminator. And what are they doing? Well, this generator, he's constantly producing some fake stuff. So it could be fake digits, for example. And we have this discriminator guy who's trying to pull apart the fake stuff from real stuff. So is that a fake one or a real one? And now these two are trained together, right? So the generator starts from some whatever white noise and runs algorithm on that, and then produces some fake. And the discriminator, he gets these two forms of input from there and from there. And for both of those has to say, was that right or wrong? And then as an ensemble, these are trained and their weights are adjusted depending on their success. Oh, actually, I need to, the plot was a bit different. So let me just finish this here now. Why is this so interesting? Well, this is interesting because in contrast to, for example, when you train with mean squared error, you have no real truth, right? So we have just these two agents, one opposing the other, but there's no objective loss function. So I'm gonna get back to that when we are there. But now I need some suspense, right? So I was just asking already for something else, right? Now, can you keep a secret? So suspense. Yeah, there's something new which I want to introduce. And actually, you guys are the first people who are told about that. I mean, it's all open on GitHub. It's not a private repository. But anyway, we really haven't told anyone. We haven't any talk anywhere about that. So, and it wasn't even clear if I was allowed to talk about that. So I asked my colleagues what they think, and yeah, they said that's a great occasion to introduce it, and I'm doing it. So we are building an R version of Torch. What is Torch? So if you're doing deep learning in Python, you probably know that Torch is the kind of main opponent to Tensor. Oh, opponent sounds negative. I mean, there's Torch and TensorFlow, right? In whatever order you want. However, when people do deep learning with Python, they normally do Torch or TensorFlow. So, and now we've been having the R TensorFlow for some years now, and that's great and that's awesome. But there are reasons to also have the ability to use Torch from R. So my colleagues started working on that. Actually, especially two of the guys you would see here. There, this is Danielle, is the main designer, and also Javier helps with that. And the guys are building an R interface to Torch. So that's the big news. And now I want to just show that already. So as I said, it's all open on GitHub, so you can basically install it, use it, but it's totally like in development state. So don't expect everything to work. On the other hand, we're also really, and I'm going to get back to that, we're also always happy about contributors if someone wants to help, etc. But let me save that for later. Let me just show how that looks, because now you've seen a bit of Keras in R, and now you're gonna see a bit of how Torch looks in R. And again, if you've done deep learning, you probably know what MNIST is. This is like normal, Roman digits, like a bit boring. But there are alternatives that is. I'm not gonna try to pronounce it because it's probably gonna get wrong. Kuzichiji, whatever, Japanese alphabet, one form of, and this looks a lot nicer, right? And it's more interesting, and we're gonna use that. And what we're gonna do is we're gonna generate stuff that looks like that, and we're gonna use Torch. So just a quick preview on how this works. And again, I'm talking a lot about Python, and this is because if you work with Python, and a lot of stuff in Torch will feel more familiar. So yeah. So but just to walk through the thing, this Kuzuchiji MNIST, this already comes with Torch. So like Keras comes with some data sets, also Torch comes with data sets, many more actually. So we don't have so many yet. I think we have 2 at the moment, but this we already have. And so you just get this data set and you already say what to do, how to transform that, right? And then another thing, I'm not going so much into details because really it's an initial stage, but you can already get a feeling how that library looks. So we have the data now. We need to load the data, and in Torch you always have these data loaders. You say what batch size to use, etc. So that's that. And then here you see how such a network looks in Torch. And here, actually, this is some sort of R6 class, looks like, but it also looks a lot like Python. So here, this initialize would be the init in Python, and forward is forward in Python. And so what do? You say this is the generator. So we have these two guys, the generator and the discriminator, and you say here in this initialize, you just say what kind of layers does it have. And this is again a sequence. Torch also has this sequential for a sequential list of layers, and these are the layers. A bit more than last time, but okay, it's like image processing and whatever. But and then this forward, there you just call layers. You could either like call some layers individually here, but what we do here is we just call this whole sequential thing. So that's the generator. Then we have the discriminator. This again looks like that too. So very Python-y, actually, Pythonic. Looks like that too. And you need a loss function, no? We said, and now we have the binary cross entropy. This is really interesting because we use that for both. And so the discriminator has to decide if it's a read or wrong input, which could be right or wrong. And the generator is then judged and trained by whether the discriminator was good or bad, or was right or wrong. And so we have a binary thing again here. So anyway, this is a loss function. And we again need an optimizer. So here both have their own optimizers in that case, you see. And this is the Adam optimizer, who I mentioned before. So Torch has an Adam optimizer too. And this is how you define those guys. Now the training looks different than Keras, definitely, at least with this Keras sequential, what we saw. And looks totally like Python, basically. So I'm not going to comment every line, but what you do is you call your model. In this case, we have two models. This gen was the generator, and there must be some disk here, this discriminator. So we call the models, we take their outputs, compare that with the target to compute losses, like this disk loss. And then we always have the sequence of these things which are used for optimization. So this really means the optimizer is going from the end of the network backward and steps through all the stuff and updates the weights. And we do this for both. So this is typical Torch. Yeah, looks the same in Python, basically. Yeah, and that's it. And just to see some output, if we start here, this is like, I don't know, perhaps 1 or 2 epochs later, 2 or 3 epochs later, again later. And as time proceeds, you see the samples are getting better and better. And at some point, I stopped training, and it's, yeah, I mean, I'm not an expert on these letters, but it looks pretty good to me. Yeah. Okay. I have no idea what time it is because I didn't put any watch here, but anyway, you will be probably thinking, what now? Well, yeah, of course, this needs a lot of, actually, when I say it needs a lot of practice, I really mean it needs a lot of practice. I don't even want to think about how long it took me to actually understand something about what was going on. But yeah, best thing is always practice. And there are lots of examples everywhere. I mean, not just our tutorials, but lots of people who write excellent blog posts about stuff. And so many people are doing that now that it's, I think, pretty easy to find good stuff to learn from. Okay, have fun, of course, yeah, and yeah, participate if you feel like. So we are always really happy about helpers, and not just happy. I think you could even say more like we really would be grateful because it's so much work. And the one thing is we have, so again, links to the GitHub stuff. This is the Torch repository. And the one thing is there's still stuff to add in core Torch. Like there are still neural network layers which have not been implemented or optimizers. But then there's also this whole ecosystem around Torch. I mean, this is probably, I don't know, depending on your experience with software engineering and your interests, as of course, there's so much stuff that builds on top of Torch. There are like Torch distributions in Python for probabilistic stuff, and many more. So so we hope we're gonna finish the Torch package sometime, but then there are so many other packages, and for sure we can't create all those packages. So it would be great to have more people working on that. That's Torch, but then of course we still have, of course, and we still maintain and will maintain the TensorFlow bindings. Here I've listed a bit more, like TensorFlow, Keras, TF datasets, but then also TF runs, CloudML. Actually, I forgot TF probability, even though I'm the maintainer of that package, so that about probabilistic stuff with TensorFlow. And there too, it's just so much that it's always great, not just to have people who perhaps feel like they could answer issues, which would be great, help with answering issues, but also there's often new features who need to be implemented. So any kind of help. And this here is a bit different. The MLverse repo, I think it's an organization, different repos where everybody could add model implementations for special deep learning models or whatever. So yeah, the thing is, we really would be happy about participation there. Yeah, and with that, I'm ready. I'm finished. So that's it. And I want to thank you so much for listening. And yeah, I'm gonna stop sharing my screen and giving back to Eric.
Hello, Sigrid.
Hey, I hear you. Hey.
Yeah. Well, sorry about that.
No problem.
That was so amazing. Truly.
Great.
You've covered the topics of deep learning, shared as an application, and much better, we are the first to hear about Touch in R.
Exactly. You're the very first people to hear about that. Exactly.
That is so amazing.
Great. Yeah, this is really a pretty big thing. It has been going on for quite some time now. I don't know. I began this year, so, and we never talked about it, and so now you know.
I hope you're not in any trouble too.
Sorry?
I hope you're not in any trouble though.
No. First, equally, not everyone was convinced that we're already at that point, but yeah, we agreed that it's fine. So I mean, so I'm not a really software developer, but software developers often are pretty perfectionists, right? So everything should be super great before one shares the information. But I don't think everything has to be perfect. So.
Okay, amazing. So Sigrid, will you be so kind to take some questions?
Yeah, sure, of course.
So we had one question.
Yeah.
Do GPUs work in R?
So again, please.
Do GPUs work in the R Keras tensor?
GPU, like working with GPUs?
Yes.
Right?
Yeah.
Should I open a chat or is it, I don't know, show conversation? Let me check, meeting chat. Okay, so at least if I don't understand anything, then there's type it there. Okay, but the answer, yeah, I mean, this doesn't really make a difference at all if you do if you use R or Python for GPU. So that works not normally, so to say.
Okay, thank you.
Okay, yeah.
So Samuel asked,
Mm-hmm.
or actually he said, great work on the torch. It already looks great. A question on the gun. Does the update on the discriminator and generator happen simultaneously for the iterations?
Well, yeah, let's say per epoch or even per iteration. If you do it batch-wise, you both update both. Actually, I could put in the chat a link. Actually, give me a second to, because I've written a blog post not using Torch but using Keras on that. It's pretty long time ago, but that's not a problem. Just to show the let me find that. Generating. Yeah, okay, so about a year ago actually, but it shows how that in principle works, and it would be similar in Torch. So I just pasted it in the Slack in the chat.
Okay, Sam. I hope Samuel has seen it. I can see it now, the link. Thank you so much, Sigrid.
Yeah, sure. You're welcome.
Yeah, so there's a good question here. Why does uncertainty matter in deep learning?
What does what matter? Sorry.
Why does uncertainty matter in deep learning? Uncertainty.
Sorry, I don't get that word. Could you just type it into the chat, please?
Oh, okay, sure. Why does uncertainty matter in deep learning? Yeah.
Uncertainty. I mean, uncertainty always matters. Okay, that's a bad answer. I'm sorry for that. No, the thing is, like in data science overall, when we make assertions, we don't really know the truth, right? I mean, even if you're asked to do a regression or so for something, and let's imagine your boss asks you to predict sales in the next quarter, yeah? And you're gonna go to say to your boss, oh, okay, my model predicts like we have an increase of 13.2% next month, and of course that number will be wrong, right? Because every concrete number normally is wrong, and so you always try to convey how uncertain that answer is, and like you say, okay, like with a probability of like 90%, it will be between that and that, and so in that way, really deep learning is no different at all. So let's take this example of these penguin classification. Let's say, okay, yeah, the network says, okay, this is I don't even remember how they were called. I don't even know, but this is this type of penguin. And then you want to know how sure the network was about that, because actually it's perhaps even a bit more important to talk about uncertainty in deep learning now that I think about it, because if you just look at the output, like you say, okay, the network said like number one was the most probable. But that can really mean that everything was totally improbable, and just this number one got a little higher score than the other ones. Okay, I realize that's the same thing for other deep learning, machine learning methods as well. But so it's always important for that reason. So does that answer the question?
I think it has perfectly done that. Yes. So I'm just typing another question we received during the RSVP. So it reads, are neural networks a silver bullet? What about other machine learning approaches such as random forest or support vector machines?
Yeah, great question. It's not a silver bullet, definitely not, but so it really has its places where it shines, especially. And so let's say historically, the big breakthrough of deep learning, I think, was around 2013, and this was with images classification. So then there are these competitions where computer vision researchers are submitting their models, and before, the most successful models were other ones, like let's say other techniques, but then suddenly neural networks start to win these competitions. And then more recently, we've seen that in natural language processing, a similar thing seems to happen. And I would say that where deep learning is performing best is all this kind of it's hard to say and how to decide how to call that, but you could say unstructured data, like not like an Excel sheet. I mean, there's a lot of data where regression will be perfectly fine, but probably not if you want to classify an image or do sentiment classification and that stuff. So I mean, there are also techniques to make deep learning more successful on stuff like tabular data, Excel sheets. So definitely there's a lot of techniques for everything always, but I would always suggest starting with the easiest thing first. I mean, if a regression works, that's great. Then you don't need deep learning. Yeah.
Okay, that was awesome. So still another question coming in.
Mm-hmm.
Very good question. So Bethany Jepchumba asks, when starting out, should one treat deep learning as a black box and learn from results, or should one go fast into the theory behind it?
Yeah, that's a hard question, really. I mean, as a black box, so I guess the way I see it is about like the talk I gave, especially not the latter part, but like the first part where I try to introduce the actors or the main stuff. So I think what you need to know is how people use words. So when something says that's an optimizer or that's a loss function, that really makes sense. I don't really think you need so much math. Also depends on your interests, but I think as long as you understand enough about it to be able to use the tutorials. I mean, if you just type in some code and have no idea what it does, then it's probably good to read more on the background. But normally, and I think for most people, and especially if you don't have the math background, it can be easiest to just basically step through tutorials first, I would say, and just do it. And then I think that has all to go hand in hand. And I think for me, it took really long to understand the concepts. And if I only had tried to read about the concepts and never tried to run such a thing, then I would never have understood it. So, so I think for most people, but I never want to say something like for everyone, because I mean, everyone's different. So, but for most people, I think it's totally fine to start with some practical stuff. Perhaps even some stuff you would be interested in. I mean, like some people like to start with something like, I mean, this is classical, like cats versus dogs, right? I mean, you could have a neural network that tells apart dogs from cats, and it could be just fun, right? I mean, if you like dogs and cats, why not, right? Okay, I guess that's my answer.
Thank you so much, Sigrid. Actually, I started with the cats and dogs, so I totally understand. I totally feel you.
Great.
Some few more questions, please. One person asked, which TensorFlow version would be a good start with new R programmers? Which one to pick from a good start to learn from, such as TensorFlow 2.0 or the new one recently launched a few days back?
I'm happy. That's pretty easy in general to answer for me, the question, because I would say that normally always when you start now, I think you should start with what is there now. Now the question is so detailed, and there has been a new version very recently. And as I said before,
I can't hear you.
Sorry, you can't hear me. You can hear me, right? What was I saying? Yeah, what I'm saying is we don't always have the R version updated to the TensorFlow version immediately, because as we're a pretty small team, and as you now know, we're not just doing TensorFlow, so there's a lot more. So, but apart from that fact, I would always use the newest version. So right now, for example, if you do install TensorFlow, the R package, and then do this install TensorFlow, you would just get automatically TensorFlow 2.2, which is not the very, very, very newest version, but nearly the newest version, so to say. And then as soon as we have the other one, but basically you don't have to decide, because if you do install TensorFlow, you will get it installed for yourself. So what I'm trying to say is you should never have the necessity to install an older version like TF2.0 or whatever, right? So right now, just do install TensorFlow. Yeah, that's.
Okay, great. Thank you. So this one question I couldn't pass, and I think I also have the same question. Could you tell us, like as a students, about how it's like out there in the AI field? Maybe what can we do to be better equipped to solve stuff using deep learning, or be out there in the industry, or how can we even help? In what skills do you have to do so that we can help? Maybe in PyTorch, TensorFlow, all those stuff, also all those awesome stuff you're doing.
Yeah, that's a very hard question, of course, because I, in general, always think that it's hard to give advice, because this is just a situation so different. So I'm trying to. I don't really. I really would. Actually, I think you probably know much better the answer than me to that question, because you know how, for example, the job market is in Nairobi. I don't even know how to pronounce it correctly. I'm sorry for that. But you know, you know, and I can't really suggest anything, right? Because I don't know what is being looked for, right? Job market is hot. I just see in the chat. That's great. So then, yeah, I don't think there's much generalizable. I mean, I think this goes back a bit to how I started my talk, that I'm getting more and more aware of how different the world is, depending on where you live, who you are. And so I think more and more that perhaps this is, I know it's not an answer, but my answer would be like, probably you yourself know best. Yeah.
It's okay, Sigrid. I think we'll skill up more and try and look what we have here in our country, the problems you can solve, and everything. I think that's what we'll do on our end.
Yeah, and for my personal opinion, and I don't really think I could say anything more than that, is that really everyone is best in the position to know what's best for them, really, in life in general. That's just my personal view. And so I never would, I find it hard giving advice in general. And oh, and now I even forgot what I was going to say. And I also think, so because that question included something, based on your journey. And so my, again, very personal opinion is that what happens in life is also a matter a lot of luck. So it's not all a matter of how good you are and how success would be deserved or something, but there's also a lot of luck in something. So I think all people can do is wish each other luck, and let me answer that. Take that as an answer.
It's all right, Sigrid. Okay, thank you for that. Could you take one more question, maybe?
Yeah.
So a person asked, it was earlier before.
Okay.
What advice would you give to people in non-math courses and would like to venture into deep learning and all?
People perhaps I can see it in the chat because you said it was in the chat. So
non-math, non-mathematics. Let me just type it in again.
Yeah.
And there it is.
I don't see it here, but in normal, I would like to have it. That I can answer better because actually I am such a person. So personally, I did not have that vast background. First of all, let me put my. Give me a second. I just have to find it. Because actually this is something I can identify with that because myself I have non-math background totally. So and I'm putting a blog post. It's already like 1.5 years I wrote that blog post. And let me tell you what it's about. It's perhaps if you're doing Python deep learning and PyTorch, you probably know this Jeremy Howard guy and the fast AI library. So it doesn't matter if you don't, but if you know who that is, then you know that this Jeremy Howard, he has an excellent video lectures on YouTube. And he has this way of just really starting with practice and not with math. And although he knows all the math very well, of course, but so just jump in. And these fast AI guys, they even let people, they build their library in a way that immediately you get good results. So you don't have to do so much yourself. And so what he said is like you learn through coding. So his kind of the opposition he draw was like you don't need to start from math. Sorry, you don't need to understand from math. Need to start from understanding the math. You can start from coding. And so my blog post was or say the main idea was, yeah, what if you're not a math person and if you're not really a code person, right? I mean, because we all do use code, like R code or Python code, but it doesn't really mean we all like are the really like the hackers, right? And so there, for me, the point is there's a third way, and this is to think about things in a conceptual way. And again, I hope this doesn't sound like an advertisement, but in my blog posts, the other ones, even the more technical ones, what I always tried is to bring about to make stand out the concepts. So it's true that sometimes I have some math in post, but actually I try to avoid it, and I always try to describe in words what's really going on. And now the question was, how can you get into that? I think only through patience and practice again. So And okay, perhaps if the question more practically, let me type something else. There, actually, the blog post has some also that, but there are some resources on the internet, on YouTube. There's the great thing is there's so much stuff we can get for free, right? I mean, with an internet connection, but otherwise, there's so many great YouTube lectures, and you have no idea how many YouTube lectures I've been watching and am still watching all the time. And there's this one guy, Gilbert Strang, who has stuff on linear algebra. And if you don't know what a matrix is or whatever, that's a great way to start, really, because this guy really explains in a great way. And the longer you do that, I think the better it works. So if I just talk about myself again, I was a newcomer to all that. I won't tell you the year, otherwise you think, oh, you will be surprised, as I started with all that pretty late. And I think I just started getting better at finding the right resources. And I really mean like online and free resources, but it takes some time. But the great thing is that there's so much stuff available, right? So I would always try it, if you look for introductory math stuff, to really find something you like. I think that's the main message. Find something you really like and not force yourself to work through something which just doesn't click. Okay, I guess that's my answer.
Okay, Sigrid. That was a really inspirational answer, truly. True. So true. We have a big number of people who are in non-math courses, and I think that will really help. So I'm waiting for more questions, because I think those are all the questions we received from the chat and from people who are RSVPing. Mm-hmm. So yeah, I think on my end, I will maybe take this chance to say really thank you to everyone maybe who took their time to be with us here. It really means a lot. And also for you, Sigrid, we don't know how to say, you really rock.
Well, thank you very much. And thank you all for your time, for listening on a Saturday evening. I mean, and yeah, I was very happy to give this talk, actually.
Yeah, and also thank you for being an amazing person.
Well, thank you for that, and I think I can return that. So from our mail exchange too, which was very nice. So thank you too for all that, also for organizing all that.
So it's okay. So maybe on behalf of the Microsoft student partners here in Kenya and the DCUT-R Data Science Club in DCUT, just once again say thank you so much to everyone who took their time to attend, and thank you so much, Sigrid, for taking us through our first steps in the planning. We really appreciate it. And maybe some final remarks before we call it an evening here.
You're asking me? Yeah, I just want to end with a thank you. So thank you so much for your time and for your interest and for the very, very nice atmosphere of this talk. Yeah, and I would want to wish you all the best, not just in these COVID times, but in general, just all the best. And yeah.
Okay, so bye, Sigrid. Thank you so much. Asante sana.
Okay, thank you. Then goodbye.